So let's maybe jump into multitask learning very briefly. So what we want to achieve is basically, and this is the first step, and I'm running a little bit over the slides if you don't mind. But as I mentioned, I'm more than happy to discuss things in more detail, maybe afterwards or in a separate Zoom session. So first step that we ask ourselves, can we do a first baby step towards multitask learning? Right? Because we have this challenge in general in audit that, first of all, I mean, we as auditors, we want to achieve a true and fair presentation or assure a true and fair presentation of our financial statements. But at the same time, we have this big data journal entries. And in order to, when we're auditing this journal entry populations, usually in the audit practice, what we have is we have demanding time budget constraints at the year end. We have extensive audit documentation obligations. And also we have strict model interpretability requirements because we need to justify somehow, for example, a certain set of journal entries that we investigated in detail. So auditors, and this was one quote of my colleagues back in the days, I mean, rather than learning a lot of different models for a lot of different audit tasks, is can we just learn a single multi-purpose model in order to accomplish, for example, different audit tasks? So can we learn rich representations of the data so that we can use a single latent space representation for a variety of different audit tasks? Maybe, for example, for audit sampling, but at the same time also maybe for anomaly detection. And therefore, we see that this is used, or this is done extensively now also in the deep learning research community. So for example, there was a recent paper that I just stumbled upon, I think, a couple of days ago, where, for example, AI researchers trained a model that is trained on two different modalities, on X-ray chest images, but at the same time on radiology reports. And ultimately, once this very similar encoder-decoder architecture converge, this model should be able to generate, based on a given input image, also corresponding description or radiology report. So we have two different data modalities that we feed in, and the model should then be able to generate such report. This has taken to an even more extreme, and there's a new research paper that was published also a couple of weeks ago by the DeepMind researchers in London, which is a subsidiary of Google, and they presented a paper named A Generalist Agent, or GATO. And this generalist agent model was actually trained on a lot of different data modalities, and the authors claim that it can perform up to 604 tasks with varying data modalities. So it can, for example, do image segmentation, can play Atari games, and also can function as a chatbot. So this is one of the ideas, and we see this direction more and more research now by a lot of different researchers across the world. And one of the key ingredients for to accomplish this is this whole idea of self-supervised or contrastive deep learning. And contrastive deep learning or self-supervised learning is somehow a machine learning technique that is in the middle of unsupervised and supervised learning on the one hand. So what self-supervised learning is doing is it's using a very limited number of labels that we have that we can easily generate, for example, by just maybe looking at a single image and then saying, okay, there's a dog contained in this image. And then based on the single image, we generate a lot of different augmentations of this image. So for example, like random cropping of the image, certain rotations, or color channel variations. And we feed these cropped or augmented images into a convolutional neural network, which is a special neural network type for images. And we learn some representations out of these images. So these are the feature extractors. So here we're extracting features out of these images. And then at the same time, we have a so-called head neural network. And this head neural network, what it should learn is actually that whenever these augmentations originate from the same image, they should attract each other in the latent space. So they should be very close to each other in the latent space. And whenever we follow up the same process for another image, like for example, as we see here for a chair, and we extract the features and also then the latent space representation, we want to again attract the representations that originate from the same image. But at the same time, as part of the learning objective, what we want to achieve is that if our augmentations originate from different images, they should repel from each other. So they should be very, very far away from each other in this latent space. And this allows us, first of all, based on all our augmentations, to encode much more data, much more information into our encodings in the latent space. But at the same time, also, it allows us to disentangle the latent space quite nicely in terms of the different data distributions that we have to train the neural network with. And then allows us, for example, for different downstream tasks like image classification to perform much more better. And this is what was also shown by the Google AI team in 2020, for example, where they showed with this architecture architecture with this idea of self-supervised contrastive learning, they are actually able to achieve on-par performance with supervised learning in this ImageNet top 1 accuracy. In the meantime, it has been proven in a lot of papers that using self-supervised contrastive learning allows to even outperform supervised learning setup. So this is a very powerful learning paradigm. So the question for us was, how can we make this self-supervised learning work for real-world financial statement audits, because we want to use at the end, or we want to learn a single model for which we can do anomaly detection, to have an interpretation of the latent space, but at the same time also do audit sampling. And one idea that we approached was we followed a very similar approach as proposed in Simply architecture and varied it, adapted it to a certain extent to the data modalities that we have in the accounting data. So again, we take a journal entry, we derive this one hot encoded representation, and we feed this then to a fully connected neural network, learn some features, and then add a projection head on top of it, which then projects these latent representations into a lower dimensional space as we see here. And at the same time, we are also applying a certain set of augmentations. So we used certain augmentations like random noise that we injected, for example, into the journal entry encodings, or cuts, or we added a Gaussian kernel on top of it. And then, since we knew that all these augmentations originate from the same journal entry, we wanted to have our original journal entry attracting these augmentations here in the latent space. And at the same time, we also applied more severe augmentations, or a so-called negative augmentation policy, where we flipped certain encoding bits here in our input journal entries. And this ultimately means that we are flipping, or we are changing a certain attribute of our input journal entry. And therefore, the semantic of the journal entry really changes, because maybe we are switching a document type or maybe a username entirely. And since this is a different journal entry then, I mean, at least in terms of the semantic to a certain extent, we want to repel from our query entry, from our original journal entry as much as we can in the latent space. So this is what we did here. So this was the entire setup. An interesting thing, if you see now this latent space representation, the first thing that we saw here in the latent space, and we used again the Philadelphia payment data set just to show and also to be able to publish it, we see this very nice disentanglement of different data attributes, for example, the payment type. So the different payment types are disentangled. If we zoom in a little bit more closer in certain manifolds, we'll see an even much more disentanglement, or for example, the fiscal month. But at the same time, if we color, for example, disentangled representations also according to accounting anomalies that have been injected, for example, we also see very nicely that the anomalies scatter out in the latent space. And also, if we apply an audit sampling approach on top on these pre-trained representations, we still can use the same representation here in the latent space and conduct some audit sampling. And one benefit for the auditors is then really that they can accomplish all these three different tasks, like, for example, to a certain extent, the explainability, the anomaly detection, but also the audit sampling on a stationary or on one single latent representation that we have been able to run. So we don't need to switch from one latent space to another latent space, depending on, for example, what kind of audit task you want to accomplish, either, for example, anomaly detection or audit sampling.